Greetings Astronomy 10 and welcome back to your One True Blue Physics lecture for this semester. Today, as promised, we're going to be covering such topics as the basic fundamentals of physics and some fundamental laws such as they apply to our study of astronomy. We're going to talk a little bit more about gravity and light and telescopes and things like that, but we'll come back to those in later lectures. Now, I want to show you today's agenda, and if you look on the left side of the board here, starting at the very top, we're going to talk a little bit about physics, we're going to talk about the metric system, vectors, conservation laws, Newton's laws, Kepler's laws, etc., all in turn. And the reason that I want to show you this to you is that if you are going to go back and watch the lecture video later, you can look at what topic we're currently on in order to fast forward, and to look to see, if you want to look over a particular topic. Because I'm going to cross these off as we go through them, okay? So that'll make it easy for you to find them. Okay, first of all, what is physics? Well, simply put, physics is the study of the physical universe, right? That's why we call physics physics, because it's the study of the physical universe. And the laws that govern it, of course, the so-called rules of the game. But physics is the study of the physical universe. In order to try to study the physical universe, what do? We make observations, we look around, right? And try to figure things out. Well, that's exactly what we do with astronomy, right? If not for the physics perspective, right, trying to use logic and technology and clever reasoning and things like that and techniques to try to figure things out, we wouldn't have astronomy, right? Like if we didn't point telescopes at the sky, we wouldn't be able to see the farthest reaches of the visible universe and try to plumb its depths for secrets. So in fact, the study of astronomy is a direct result of the study of physics. So it's important for us to learn a little bit about physics, right? So let's begin at the very beginning. If you wanted to try to make some observations about the world around you, what could you do? How would you go about it? If you want to just observe stuff, right? Things, people, places, things. You might say, oh, what's this? Okay, obviously this is a whiteboard eraser, but what are its characteristics? What make it different from, this ruler? Well, this has a certain amount of heft to it because it has a certain amount of, particles and matter and stuff that make it up, right? But it also has, a certain length, width, thickness, right? However you want to think about it. And so you could take measurements of these kinds of phenomena, right? Now the basic ones that we just talked about, there's actually a thing called mass, which is different from this thing called weight. Weight is different from mass, okay? These are two totally different things. And then also we talked a little bit about length. There's another one that we measure all the time that's a little bit subtle. And I already said it, it's time. These are some really basic things that we can observe, right? Now let's be really, really careful as we talk about these. Mass is the amount of particles and matter in a substance or an object or a person, place, or thing, blah, 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 right? But that's different from weight. Weight is the force of gravity on an object, okay? The stronger gravity is, the greater the weight is. All of the bathroom scales that you have or whatever in your house, if you have a scale, right, It's actually telling you your mass because they're calibrated against surface gravity. You would have a different weight on the moon because gravity is different there. But you would have the same mass because you're still made up of all the same stuff, particles, matter, stuff. Okay? So that's the difference between the two. Now the basic unit that we use in science, you might say the gram, but that's actually a very, very small mass, right? That's the amount of sugar that's in one of those little paper packets, right? Usually for things that are closer to our, what we call macroscopic scale, we use a unit called the kilogram, which is actually 1,000 grams, right? And then 1,000th of a gram is this thing we call a milligram. This is usually the amount of dosage that you get in your medication, right? If you've ever had to take medication, you'll have a tablet that's 100 milligrams or 20 milligrams or blah, 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 right? Okay. We also talked a little bit about length, right? Standard of unit of length, excuse me, is the meter. Now, for distances in between, like cities or neighborhoods or whatever, you might use the kilometer, which is 1,000 meters, right? And then, if you want to talk about a really, really small distance, right, you talk about a millimeter. That's not the difference here in between the 5 and the 6. There's 10 millimeters in between there, right? One of the really, really small things. And it's hard to see, it won't focus at this distance, but that's a millimeter, right? It's 10 to the minus 3 meters, if you remember your scientific notation, or 1,000th, 0.001 meters. But conversely, a kilometer is 10 to the 3 meters, 1,000, right? The same is true for grams, kilograms, milligrams. Time, of course, doesn't really kind of work like that so much. We usually use seconds. Sometimes use minutes or hours or days or, whatever you need to. Now here in the States, our standard unit of mass is the pound, which is made up of 16 ounces, right? And then there's 2,000 pounds to a ton, and there's 12 inches in a foot, right? 5,280 feet to a mile, or 1,760 yards. It's crazy, right? This is so much simpler. Not to mention, the original definition for these units goes something like this. If you had a cubic enclosure that was 1 centimeter on a side, it's a cube, right? So all the lengths are the same. This would have a volume of 1 cubic centimeter. In medicine, sometimes they call that a cc. Okay? Now, if this was 1 cubic centimeter of water, H2O, at standard temperature and pressure, 1 atmosphere at 20 degrees C. 1 cubic centimeter of water would have a mass of 1 gram. That's where this comes from, this whole metric system. That's the original definition. Nowadays, we use a certain wavelength of electromagnetic radiation for the meter. I believe it's actually in the radio band, but you commonly think of electromagnetic radiation as light. Nowadays, we also use, there's a certain crystal, and we use its vibration to track, to get our definition for the second, right? It's like 0.0015 vibrations of a cesium atom or something. That's our definition for the second now. It's much more concise than our old one. So we have really, really good stuff nowadays, but this is the original definition, right? In any case, that's the basics of the metric system and why we don't use the imperial system in science. Some people still, like to try to go against the grain and use the imperial system, and that often has disastrous results. Not that long ago, we built a satellite called the Mars Climate Orbiter, and one of the defense contractors, Lockheed Martin, who was working with NASA on this project, one of their engineers was using feet instead of meters. And as a result, we lost the Mars Climate Orbiter, several $100 million worth of really sophisticated electronic equipment, science stuff. It was called the Mars Climate Orbiter because it was supposed to go to Mars and study the climate, the atmosphere, things like that, and we lost it. So from now until the end of time, as far as this class is concerned, we will only use the metric system because that is what we use in science. Okay? Alright, before we go on any further, it behooves us to discuss a very scary mathematical quantity. Okay? The vector. You ready? That's it. It's an arrow, okay? It's a straight line, has a start point and an end point, and usually like an arrow to tell you which way it's pointing. That's it. Scary, right? Okay, what's the difference between this vector and this vector? Let's pretend they're pointed in exactly the same direction. Well, obviously, this one is much longer than this one, right? We'd say this upper one here has a greater magnitude. That's our first criteria. Okay, now we're going to pretend, because, I was forced into a life of science because I can't draw to save my life. But we're just going to pretend that this next vector I draw is exactly the same length or magnitude as this next vector I draw. Okay? Well, it's not bad. Now what's different between these two? Assuming they have the same magnitude. Well, this one's pointing this way and the other one's pointing that way, right? So you could say that these have different directions. Okay, that's what a vector is. It's an arrow, a straight line that has a start and an end. It has a magnitude or a length. It has a direction, right, where it goes from start to finish, that way. That's it. That's a vector. Okay, well, why do we care about vectors? Well, it just so happens that a lot of very useful quantities are vectors. I'll show you what I mean. Let's say you wanted to talk about the position of this blue pen. Where is it? It's right down here, right at the bottom of the screen. Where is it? Aside from being at the edge of the screen. You might say that it's about 25 centimeters in front of the board, this direction, right, in front of the board. Or you might say that it's about 20 centimeters this way from this piece of electronics in the red pen, right? Now, is it possible for you to describe the position of this blue pen without talking about the position of something else? Think about it for a second. Absolutely not, right? It's impossible. So in order to describe the position of something, you have to have a reference position, right? And if you want to talk about where something is, you talk about where it is relative to this other thing. It's on top of the couch, it's in front of the board, it's this way from this stuff, blah, 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 right? So the position of an object is defined as a vector. And that's just the warm-up. So there's this thing that we call velocity. Oh, by the way, What is the standard unit of measurement for a position vector? It has a length, right? What do we measure those in? So the unit for position is the meter, right? It's this many meters from this point. This other thing that we're probably not used to thinking of in quite so many words, this thing called velocity. Now, if you're driving in your car and you look at your speedometer, does it tell you your velocity? Actually, it doesn't. Velocity is a vector, and therefore, it has to have two pieces of information, right? The magnitude and the direction. And if you look at your speedometer is just telling you how fast you're going. That's the magnitude, right? It doesn't tell you what direction you're moving. You'd have to, look at a compass or look out the window, hopefully, and know where you're driving. That would be good. Right? And so, if you have some velocity, right, if you're moving in this direction, sometime later, you'll be here instead, right? So you're going to go a certain amount of distance in a certain amount of time. That's why the units of measurement for speed in your car, in your speedometer, are something like miles per hour. There's also usually another ring that says kilometers per hour, right? Now what that means is your velocity is the distance that you travel, miles. Just this one time I'll use miles, just to make it easy, because we use miles every day. Miles per hour, right? You go a certain number of miles in a certain amount of time, right? Number of hours. For example, if you travel at 60 miles per hour for 1 hour, you go 60 miles, right? You might use kilometers per hour, right? That's the same thing except with clicks instead of miles. But if we were going to use the SI units, remember our MKS units? What's the basic unit of measurement for velocity? Well, we got a distance that's meters, and we have a time that's seconds, right? Meters per second. Actually, 1 meter per second is about 2 miles per hour, sort of back of the envelope calculation. And so they're not that far off. So this is usually the standard unit of measurement that we use, right? Sometimes, you use kph, whatever, you're driving your car, but usually we say meters per second. Right? So velocity is also a vector. There's also a thing called acceleration. And it has its own unit as well. Now acceleration goes something like this. If you're in your car and you're driving, okay, this is your velocity. If you hit the gas, what's going to happen? You're going to go faster, right? So your velocity vector is going to increase, right? That means your velocity vector changed. It got bigger, right? It accelerated. Now, you can accelerate really fast and change your velocity a lot in a small amount of time, or you can accelerate really slow, changing your velocity just a little bit over a really long time, right? You could also hit the brakes, right? What would happen then? You would slow down, right? You would accelerate backwards. It would make your velocity vector smaller, right? If you hit the brakes, you would slow down. So it seems to me then that acceleration, because it's change in velocity with respect to time, Our velocity has units of meters per second. Time has a unit of seconds. That boils down to meters per second, or meters per second squared, right? Meters per second per second. That's our unit for acceleration. Surface gravity has an acceleration of about 9.8 meters per second squared here near the surface of the Earth around sea level. Okay, now I talked a little bit about accelerating forward by hitting the gas and accelerating backwards by hitting the brakes. But what would happen if I turned the wheel? I would then be accelerating, I'd turn the wheel to the right, and so I would accelerate to the right. If you're going this way, you turn your wheel to the right, and you start to turn, right? And so what's going to happen? Your velocity vector is going to change, you're going to go down, and assuming that you keep holding the wheel such that you keep turning at a constant rate. It doesn't look like a constant rate, I'm sorry, it should look like a circle, but I can't draw to save my life, so I hope it comes across. But in any case, if you just hit the cruise control, right, or just, keep your foot exactly in the same place on the gas pedal so that you go the same speed, but you turn the wheel, right, and you turn it at a constant rate so you just make one circle, right, one perfectly even circle. What direction are you accelerating towards? Are you accelerating backwards or forwards? Are you accelerating? Well, yeah, you're changing your velocity, right? Velocity is a change in position over time. Acceleration is a change in velocity over time. Well, we're turning the wheel to the right, right? So to the right, and then here, when the velocity is this way, we'll be turning to the right, and here we'll be turning to the right, and here we'll be turning to the right, towards the center of the circle. As a matter of fact, for an object to be moving in a perfect circle like this, like in a stable orbit around a planet or a star or something like that, let's say now that instead of, this being your car, let's say there is a satellite in orbit around, everybody remember what this means? Planet Earth, okay? So there's a satellite in orbit around planet Earth. Gravity's pulling it down, right? And it's going to move this way, and it's going to go around the circle. Gravity is still pulling it down towards the Earth. Here, gravity is still pulling it down towards the Earth. Here, gravity is still pulling it down towards the Earth, right? Always towards the center of, in this case, the orbit. So, suffice to say that if some object is going to move in a circle, try to get it here in the middle, make it slower so you can see it a little more easily. Something is going to move in a circle, it has to be constantly accelerated towards the center of that circle. In this case, why is this thing moving in a circle? Because my hand is swinging it around, right? What's pulling it? My hand. Where is my hand? It's in the center of the circle, right? So suffice to say that things can only move in circular paths, right? They can only take circular paths if, sorry, I'm trying to make sure that Ninja doesn't destroy the rope over there. Ninja. Ninja. It's not a toy. Don't play with that, please. Okay. No, Ninja meows. Ninja. Oh, here comes Lucky. Now you think I'm going to go behind that and play with cats. Anyway, where were we? Ah, right. anytime an object moves around in a circle, if it's accelerating towards the middle, and it has to, right, in order to stay moving in a circular path, it accelerates towards the center. We call this centripetal acceleration. Or center-seeking acceleration, right? Centripetal. Now, it just so happens that for every radial distance, there's a certain velocity that you need to maintain, but I would never ask you to try to solve something like that, so we won't get into that. We will come back to this just a little bit, however, when we talk about the slingshot or gravitational assist maneuver and the use of probes and things like that in order to try to, you know, investigate the solar system. Okay. Now, if an object is in space, right, gravity is pulling it downward. It's exerting a force on it, right? What is a force? Is it a Jedi's power? What is a force? Well, if I were to apply some force to this board, I could move it, right? I could also pull on the board a little bit and exert a force on it, and that could also move it. Push it this way, that way, lift it, throw it, whatever, right? Pushing it or pulling it, essentially. And so a force is basically best defined as a push or a pull. Now, you can push or pull in any direction. You can push or pull with a great amount of strength or a small amount of strength. So force actually also is a vector, right? Sorry, cats. So essentially, lots of useful units of measurement and quantities are vectors. Oh, that'd be meow. Anyway, that's enough for the fundamentals for now. Let's talk a little bit about conservation laws, shall we? Okay. We're going to talk about conservation laws. You should know this. If there is indeed anything that you're going to get out of today's lecture, maybe even anything from this entire course, it is this: that there are symmetries in nature, and from these symmetries arise what we call conservation laws. Now, there are actually more than just the three we're going to talk about today, but there are several conservation laws. Now, in order for us to talk about what a conservation law is, or what these conservation laws are, we need to talk about what it means to be a conserved quantity. So we'll start with the most simple example, the law of conservation of matter. Simply stated, the amount of matter in the universe stays roughly the same. The simple example, similar to that we all learned in grade school, was that thing called the water cycle. Everybody remember? So water will evaporate, go up into the air, make clouds, and then it'll come back down and rain. You know, maybe you'll drink it, and then it comes out as sweat, or blah, 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 right? Basically, the amount of water here on the surface of the Earth stays about the same. And so, it's a conserved system, right? But an even bigger one is that all of the matter in the universe, the amount of matter in the universe basically remains the same. So all of the protons, neutrons, electrons, all of the iron and steel and diamonds and everything in the universe is made up of all these little particles, protons, neutrons, electrons. Those are made up of quarks, and those are made up of things that we're not even really sure we understand yet. But the amount of all that stuff, all of the matter in the universe, roughly remains constant. It may change forms, but the stuff is still there. So that's our first conservation law, the law of conservation of matter. The second one is something that we call energy. Now, energy is kind of a funny thing because it has sort of an interestingly circular definition. Energy is the ability to do work. Work is an activity that requires energy to do. So work is like if you apply a certain force, you push for a force of 10 newtons in this direction, then, if you push over a certain distance, right, the greater that distance, the more work you did. Right? And you need energy enabled to do that work in order to try to, move this object, right, or apply this force, however, whatever you did. A simple, or a couple of simple, examples of energy, if we want to talk about the really, really simple ones, we've got kinetic energy, or the energy of motion, and we've got potential energy, right? In our case, we're going to use gravity. Okay, so gravitational potential energy. If you have some object here, right, sitting on this spinny chair, right, it doesn't really have a lot of energy, it can't do a lot of things, it doesn't have any, chemical energy like in a battery or any electrical energy like what powers in your house. But if I pick it up, it gains some gravitational potential energy, right? The higher I pick it up, the farther it can fall. Now, if I just pick this object up and drop it, it kind of seems like all the energy is gone now, right? Where did it go? Well, as this object gets dropped, it falls, right? It falls faster and faster and faster until finally it hits something, and somehow changes its velocity, right? Its acceleration, whatever. And so this gravitational potential energy, as it falls, gets converted into the energy of motion, kinetic energy. And until this object interfaces with another system, the amount of total energy this object has stays the same. Up here it has a bunch of potential energy, but no kinetic energy, right? Is it moving? No, not at all. It has no kinetic energy, right? It's not moving. But all the way down here at the end, it has no more gravitational potential energy. It really can't fall any farther. But it's moving fast, right? So all of that gravitational potential energy becomes kinetic energy as an object falls. And essentially, the amount of total energy that it has as it falls stays the same, and so energy is conserved. Now when this object hits the chair, obviously it doesn't have that energy anymore. Did it get destroyed? That would violate our law of conservation of energy, right? So what happened? Well, listen. You can hear it fall. So some of that energy became sound. If I drop this object in the same spot 100 times, or whatever, would it be warmer there? Yeah, of course, friction, right? And so that energy came from somewhere, from the object falling and transferring it, right? Now most of the energy probably went into, making this huge chair bounce just a little bit, right? And that'll send vibrations into the floor and blah, 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 until it gets damped out really quick, because this is, made of solid matter. But that energy went into this system now, the floor and stuff, the building. And so that energy didn't get destroyed, it just went in between systems, right? So energy can change forms, it can change systems, but the amount of energy in the universe basically stays the same. That's the law of conservation of energy. Now, once upon a time, we used to think that these things were separate, right? Until a guy named Albert Einstein came along and said this. E equals, it's supposed to be an M, mc squared. What does that mean? Energy equals mass times the speed of light squared. Matter, mass, right? Energy, E, is equal to mass times the speed of light squared. Now the speed of light is 3 times 10 to the 8th meters. It's a big number. It's the fastest thing in the universe. Squared is 9 times 10 to the power 16. That's a way, 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 way bigger number, right? So if you have a small amount of mass, you can get a huge amount of energy if you convert that matter into energy. And that is how stars power themselves, because there is a slight amount of nuclear binding energy in a helium atom compared to the 4 hydrogen atoms that make it up. And that small energy difference is more than enough to power a star. Call it nuclear fusion. We'll come back to that. But suffice to say, if you took about 1 gram of pure hydrogen and you converted all of it into helium, it would be about the same amount of energy as 10 of those Moab, whatever, daisy cutter bombs. It's huge. That's what this equation means, right? E equals mc squared. This is a very big number. Now, we used to think that these two things were separate, but there's an equivalence in between them. And this is why we call things theories, because these are not wrong, right? That's not the point, but they just so happen to be part of a larger picture. And sometimes as we learn new things about the universe, and we find new, better ways to describe them, we realize how right we were to begin with sometimes. Right? And that's why we call things theories, because they evolve over time. In any case, there is one more conservation law, this thing we call momentum. And momentum is defined to be, that's what the triple equal sign, the 3 equals. Momentum is mass times velocity. What does that mean, and what does it mean to say that it's conserved? Well, okay. First of all, if you want to think about building up momentum, you know that you have to like run faster or whatever to build up momentum, right? Obviously your velocity is part of that, right? The faster you go, the more momentum you have. But also, who has more momentum? Somebody in a truck or the same person on a skateboard? What is the difference between these two situations? Well, the person in the truck has a lot more mass, right? And so if they're both going 5 meters per second, the person on the skateboard and the person in the truck, the one in the truck obviously is going to have much, much more momentum. Think of it this way, right? You have a goofy little picket fence or a scrawny chain link fence or something like that. And the person on the skateboard and the person in the truck both collide with this fence going at 5 meters per second, about 10 miles an hour, not really fast. Okay? What's going to happen? Well, that person on the skateboard probably is just going to bounce off of the fence, and the truck is going to go right through it, right? Because the truck has a lot more momentum because it has much, much more mass. Okay? Now, in order to say what it means to say that momentum is conserved, we're going to perform a very famous thought experiment. Okay, this is a couple of train cars. So here you have one train car with mass m moving with velocity v. Okay? It has a certain mass, whatever it is, 1,000 tons, whatever, and it's moving with a velocity 5 meters per second, whatever it is, okay? So its momentum is its mass times its velocity. Okay, And it's going to run into a cart, another railway car, right, that is not moving. No velocity, right? Velocity is 0. And when they collide, they're going to hook together. Okay? And then they're going to move off with a new velocity v prime. The apostrophe there makes it a prime. These are still the same cars, so they still both have a mass m. What's happening again? Well, we have one car moving along a railroad with a mass m and velocity v, and we have an identical car with the same mass standing still. And they collide. And in so doing, they hook off together and roll away. Okay? Now, if we're going to say that momentum is conserved, we would want to say that the momentum before the initial momentum, right, the momentum of these two things, this car moving and this car standing still, total momentum here equals the final momentum, right? Because the momentum has to stay conserved in this system, right? Now what's the original momentum? Okay, this has a momentum of its mass times its velocity, right? So this car has momentum mv, right? It has mass m, velocity v. Okay, what's the momentum of this car? Well, it has mass m, but it has a velocity 0, right? So it has no momentum. So the total momentum before, right, because only this thing is moving, is mv. Afterwards, how much mass is moving? Both of them, right? They hook together and they move away, right? These two carts hook together and move away. So this has mass m, this has mass m. We're talking about mass 2m, right? What's the velocity? We called that v prime. All right, I'm going to rewrite this equation just a little bit to clean it up just a little. We said mv is equal to 2mv prime. Okay, this is what we call an equation. It's an equation because what's on this side equals what's on this side. It's like saying 1 equals 1. It's a true statement, right? And so is this, because momentum is conserved. Okay, now if you want to try to change an equation, you have to do the same thing to one side as you do to the other, right? Like, if you added 10 to both sides, this would say 11 equals an 11, and it's still a true statement, right? You could multiply both sides by 10, it'd be 10 equals 10, and it would still be a true statement. You could divide both sides by 10, 1/10 equals 1/10, and it's still a true statement, right? So you have to do the same thing on both sides, otherwise it's no longer an equation, right? Okay. So if we want to try to figure out what v prime is, or how fast these cars are moving in relation to the old velocity, we're going to have to change this equation around, right? Ideally, we want to get this by itself. That seems to help. So let's start by dividing both sides by m, shall we? We can do that, right? It's still an equation. If we divide both sides by m, we can do the same thing to both sides. Well, what's m divided by m? Well, anything divided by itself is 1, right? A million divided by a million is 1. 10 divided by 10 is 1. Okay, so that's 1, that's 1. So then this is just 1 times v, or v, right? And this is just 1 times 2v prime. To make things really, really simple, let's divide both sides by 2. 2 divided by 2 is 1, that gets rid of that. And v over 2 is v prime. And now the punchline, okay? The final velocity of the system, the speed of these two cars after they hook up together, right, the magnitude of this velocity, is equal to half of the velocity of this one car moving by itself. Why? Well, when they collided, now twice as much mass is moving, right? In order for momentum to stay the same, if the mass is going to increase, the velocity has to decrease. And so these two objects, when they hook together, they move off at slower than this object was going by itself, right, with half the mass. We double the mass, we have the speed, and momentum is conserved. Now that's what we call linear momentum. There's actually also a thing called angular momentum. And angular momentum, unlike linear momentum, is defined this way. It's L MR, right? I'm sorry. Angular momentum is MVR. Now what does this mean? Well, at this point, you might want to hit the pause button and go and look at the turntable demo that I've linked in on today's lecture page. The turntable demo. Angular momentum is generally defined this way, right? You get an object moving around a circle on a circular path, right? Going around this circle. Then it has a certain radius or distance from the center of that circle, right? At all times, it has this radius r. That's this part. Now it's also going to have a certain amount of velocity, right? Here it's going to be going this way, here it's going to be going this way, here it's going to be going this way, and it's going to go around the circle. But angular momentum is mass times this velocity times radius quantity, right? So an object that has a lot of mass is going to have a lot more angular momentum than something really small. Okay, and if we remember the turntable demo, if you have an axis of rotation here and you have some object moving around with a certain velocity, right? Its mass isn't going to change if it moves in and takes a smaller radius, right? Moves along a smaller circular path. So if the mass doesn't change, in order for momentum to be conserved, the radius is decreasing, right? That means the velocity has to increase for angular momentum to stay the same, right? And that's why, as this radius decreased from this big one to this small one, and the person brought the weight closer to their body and their axis of rotation, right? The radius decreased from this big thing to this little thing, right? It decreased. So the velocity had increased proportionately and ended up spinning really, really fast. Momentum is conserved. In this case, angular momentum. Okay, that is our conservation laws. And if you're going to get anything out of today's lecture, at least let it be that. Now let's talk a little bit about how things move. We've talked a little bit about, actually we talked a little bit about how things move. Let's talk a little bit about why things move, or Newton's laws of motion. In about 1700, a guy named Sir Isaac Newton came up with some very simple rules, guidelines for describing the way that things move. Nowadays we call them Newton's laws of motion, and the first of them is this funny thing that we call the law of inertia. That's supposed to be an E. Now the law of inertia basically says that an object at rest remains at rest unless acted upon by a net external force. And an object in motion in a straight line with a constant velocity will continue on as such unless acted upon by a net external force. Now there are a couple of key words there, net and external. A net force, the meaning of that word goes something like this. If we look at this eraser, it's sitting here on this spinny chair, okay? What forces are acting on it? Is gravity pulling it down? Yeah, gravity is holding it to the chair, right? So here's the chair, here's this thing, our mass, our whiteboard eraser, okay? The force of gravity is pulling down on it, right? Well, if it's being pulled down, how come it's not accelerating towards the center of the Earth? That's the only force acting on it, right? Oh, but it's not, right? The chair is holding it up. We call that the normal force, because normal, according to mathematicians, means perpendicular to the surface, right? So this is the normal, right? It's perpendicular to this surface, points straight away from it. And so the normal force is perpendicular to any force of contact. When any two things come into contact, they exert a normal force on each other, right? Perpendicular to their surfaces of contact. So we got gravity pulling down, we got the normal force pulling up. These are equal in magnitude and opposite in direction. So when we add them up, this could be like, 1 Newton, and this could be like 1 Newton. But when we add them up, because they're in opposite directions, we get 0. You can think of this as +1 and this is -1 or something like that, and you add them and you get 0, right? Because they're in opposite directions, they have the same magnitude, and therefore this thing is neither accelerating towards the center of the Earth or flying out into space. The forces add up to 0. So the net force is 0. What about if I pushed it by applying a force to it, but I didn't push it far or hard enough so that friction made it stay in place? Push it, but not hard enough to move it, right? So you apply a force, but then friction applies an equal force. And even though there are 4 forces on it, when I push, friction is fighting me, gravity's pulling down, the chair is pushing up on it, right? These two are also equal in magnitude and opposite in direction, so they add up to 0 also. Again, the net force is 0. So far we've had 2 forces and 4 forces that add up to 0. What if we had 6 forces? 2 more forces that also added up to 0. What's the net force? Still 0, right? What if you had 1,000 forces that when you add them all up, you get 0? What's the net force? Still 0. That's what we mean, the total force on an object. If you add up all the forces on it, a net force. Now, external is important because only an external force can accelerate something. Let's say you wanted to try to pick yourself up by your shoelaces and make yourself levitate. Could you do it? No, of course not. That's impossible, right? That's crazy talk. If you do, you're just going to pick yourself up and rotate yourself over and probably fall. That's an internal force. That's you applying a force to yourself. And so you cannot accelerate from an internal force. You need not only a net force, a total force, in order to accelerate something, but it also has to be an external force. Something else has to push you in order for you to move. Now, is that true? You kind of feel like, no, you get up on your own, right? But no, you push on the floor actually pushes on you. Right? So you need a net external force in order to change something's velocity, in order to accelerate it. Right? You have to push the pen for it to move. You have to drop it or whatever for gravity to take it over. There has to be a net external force in order to accelerate something. The second of these laws is commonly known as F equals ma. This is like the really, really short version. So we're just going to keep it simple. Okay? What does this mean? Well, I like to think of a pebble and a boulder. Okay? If you have some tiny little pebble, it has a certain amount of mass. Right? And if you pick it up and you throw it. Are you going to be able to make it accelerate more than if you picked up a huge boulder? Which one could you throw faster or accelerate more? Which one could you throw farther, right? Well, a tiny little mass, you can pick up and throw easily. But a really big one, not so much, right? That's basically what Newton's second law means. If you apply a force to an object, right, you have a certain amount of force that you can exert on a rock that you throw because you have a certain amount of physical strength, right? So you can apply a certain amount of force. If you apply that force to a very big mass, it's not going to move that much, right? No matter how strong you are, you probably can't be pushing boulders. But if you apply the same force to a smaller mass, a little rock, you can accelerate it a lot more. You could probably throw it, right? That's essentially what it means, if you want to think of it that way. Now this is an equation, and so we're going to do a couple of things here. Let's say we divide both sides of this equation by m. Okay, we divide both sides by m. Here we're going to get f over m. And then we're going to get m over m, which is just 1, and then a. F over m equals a. Well, that's what I just said, isn't it? The amount of acceleration that an object is going to feel, right, the rock, the boulder, is going to depend on how much force you can put into it, and also on how massive it is. The more massive the object is, the less acceleration you're going to get. The more force you apply, the more acceleration you're going to get. That's what this equation means. Now you could also divide both sides by a. F over a is equal to m. And if you want to think of it this way, mass is how much resistance to acceleration there is from an applied force. You have to apply more force to get the same acceleration from a larger mass. If you want to think of it that way. Any way you want to think of it is fine. Just so you've seen it once, the unit for force is newtons. And Newton is a mass times an acceleration unit, right? A kilogram, obviously, from mass. Acceleration is meters per second squared. So a newton is, or the standard unit of force, is a kilogram times meter per second squared. F equals ma. The third law is a funny thing that we call the equal and opposite law. It is commonly bastardized as for every action there's an equal and opposite reaction, and that is wrong. Okay? What it really means is that forces always occur in pairs, equal in magnitude and opposite in direction. Okay? If you push on something, that means it should push you back, right? If forces always occur in pairs, equal in magnitude and opposite in direction. Well, if I stand over here by the wall and I push on the wall, I push myself back, right? Now I know some of you are thinking, oh no, that's not convincing. Well, I tied this rope to the door. Let me just pan the camera just so you can see the door a little bit better. Actually, I think it's pretty good. This is a glass door. You can kind of see the handle here. And in any case, I'm going to pull on it, and what happens? The line goes taut, right? Now, I know all of you have probably played tug-of-war at some point in your lives. So you know that ropes can only go taut if how many teams pull on them? You need to have an equal amount of force pulling this way as this way, right? This is called a tension, by the way, if you have a force in like a rope or a line or a string or whatever. Well, I'm pulling on the door is pulling on me, so the force, as long as this thing is taut, has to be the same, right? So I'm pulling on it, it's pulling on me. And if it wasn't true, if that was not the case, then you've never seen tug of war being played. It takes two teams to pull on a rope to make it go taut. If only one team pulls on the rope, it goes slack, right? So there has to be an equal and opposite force on both ends of the rope. And long story short, if I pull on the wall or on the door, it pulls back. If I push on the door, it pulls back. Or it pushes back, right? Forces always occur in pairs equal in magnitude and opposite in direction. But wait, what about gravity? Gravity is a force, right? So if I drop this, gravity pulls the pen downward. But then shouldn't the pen's gravity pull the Earth upward? Well, it does, actually. Gravity is a mutually attractive force. These two masses are attracting each other. And the closer they get, the stronger the gravitational attraction is, right? But if that's true, then how come the Earth doesn't move when we drop the pen? Well, which one is more massive? Right? They feel the same force, but you're talking about a tiny little force to move this pen. And it would take a very, very, very massive force, like the attraction to the sun, because the sun is more than 1/3 of a million times the mass of the Earth. What's going to move the Earth more? The sun or this pen? Long story short, it does feel the attraction, but it just doesn't move it much because the Earth is so much more massive. Now, if I was going to ask you exam questions on this stuff, you would probably just have to know the definition of inertia. If I was going to ask you an exam question on Newton's second law, it would be something simple, like if you applied a force of 10 newtons to an object with a mass of 10 kilograms, what's the acceleration? So then you could just solve it. You'd say F equals ma. Force is 10 newtons, mass is 10 kilograms. A has to be 1 meter per second squared because 10 times 1 is 10. Or, if you want to be methodical about it, you want to solve for the acceleration, right? So you divide both sides by m. You get F over m equals A. Your A is 10, or your force is 10 newtons, your mass is 10, is 10 kilograms. 10 divided by 10 is 1, right? And so your acceleration is going to be 1 meter per second squared. Remember, newtons is kilograms times meters per second squared, so you divide the kilograms out, you get meters per second squared. If I was going to give you an exam question on Newton's third law, it would be something like this. Let's say you're an astronaut. You're out in space, you get your space helmet. And you're out, repairing a satellite or something. Those are its big solar panels. And as you're out doing your spacewalk, repairing the satellite, you lose your grip on it, you slip away, and you start to drift off into space. Now normally that's a death sentence, but you happen to have a tool belt, and so you have like, a wrench. God, that's a terrible wrench. Looks more like a tuning fork. Okay, so you have a tuning fork, right? And you need to get back to the space station or, the satellite, whatever it is you're working on, Otherwise, you're going to slowly lose your oxygen and die out in space. So what do? Well, if you were out in space with this huge tuning fork, if you threw the tuning fork this way, you would be applying a force on the tuning fork that way, right? Does that mean that the tuning fork would apply a force on you this way? Well, yeah. Forces always occur in pairs equal in magnitude and opposite in direction. You push the tuning fork that way, it pushes you this way. And that should accelerate you back towards the space station or the satellite or whatever it is you're working on. Now, if you threw this tuning fork with a force of 50 newtons, how much force would it apply to you? Same thing, 50 newtons. Dun, 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 dun. And that is the equal and opposite law. Newton's third law of motion. Okay, let's talk very briefly about Kepler's laws of planetary motion, of which you may have guessed it from the fact that there were 3 key vectors and 3 conservation laws and so on, that there are 3 of Kepler's laws of planetary motion. The first of these is that planets generally don't move in circles, they move in shapes called ellipses. What is an ellipse? Well, let's say you had a piece of string, okay, and it was a certain length. And you took one end of the string and you put it through into like a board or something with a thumbtack so it would hold there. And then you took the other end and you put that on a thumbtack, right? And so there's this piece of string kind of hanging in between these 2 thumbtacks, right? And you take a pen or a pencil or something like that and you pull the string all the way out. And you drag it all the way around. And it makes a shape that looks kind of like this. Okay? The dictionary definition of an ellipse, or I guess the mathematical definition of an ellipse, is it is the locus of points whose distances from 2 focal points sum to a constant, right? The length of the string, right, these 2 lengths from the 2 thumbtacks to the 2 focal points, always add up to the same length, right? It's the same string. These 2 lengths together always have the same total length. And so all of these points are distant from these 2 focal points such that they sum to a constant, right? That's an ellipse. Now it just so happens that if you were going to try to draw this as the Earth's orbit, these 2 focal points would be like right next to each other, right? And if you only have 1 focal point, you have a perfect circle, right? Because the distance is the same the whole time. As a matter of fact, the Earth's orbit is only about 1% different from a perfect circle, right? It's almost a perfect circle. So this elliptical representation doesn't actually fit our solar system so well. Most things have an eccentricity of 5% or less, some of them have maybe 10. So it's maybe 5% different from a perfect circle. Not like this. This is, a lot. Anyway, ellipses have the following anatomy. This long side, from this end to this end, is called the major axis. This shorter one is called the minor axis. Half of the major axis is called the semi-major axis. And this distance is the average distance from one of these focal points to the ellipse. It's less here, it's more there. This is the average distance. The semi-major axis. Okay, that'll be important later. Now, Johannes Kepler, if you remember, he was able to prove that this is how planets moved, right? He had the mathematics to back all of that up. That was his first law of planetary motion. His second law is called the equal area, equal time law. And that goes something like this. So let's say you have your elliptical orbit, okay, and this is one of the focus points. Some object, let's say this is now not a thumbtack, but let's say this is the sun. Okay? Whenever you see the circle and a dot with it, that's the sun. And let's say this is, some planet, right? Now in 1 month, the planet is going to move from here to here in its orbit. The position vector of this planet relative to the sun, right? The distance from the sun to here in this direction, that's its position vector relative to the sun, right? And this is its position vector 1 month later. Now during that month, this position vector is going to sweep out a certain amount of area. Okay? Now later on, when the planet is closer, because of the increased force of gravity, this thing is going to move a greater distance in 1 month along the circle, or the ellipse, excuse me. And so the position vector is going to sweep out this area instead. But these two areas are the same as long as the time in between these 2 points is the same. If it takes 1 month to go from here to here, but also from here to here, the position vector is going to sweep out a certain amount of area, and in these 2 equal amounts of time, it will sweep out an equal amount of area. Now, strangely enough, if you remember from our conservation of angular momentum, when the object is further away, or when the radius is bigger, the velocity is smaller. And when it's closer, right, when the radius is smaller, the velocity is bigger. Look, it moved much farther, right, in that month. And so really, this equal area, equal time law is a restatement of our law of conservation of angular momentum. But Johannes Kepler didn't know that at the time. Okay, finally, there is a very simple relation in between what we call the orbital period, or the amount of time that it takes for something to make an orbit, and the orbital semi-major axis, or the average distance from a planet to the sun. And if we use just the right units, there happens to be a very nice relationship in between these two numbers, the orbital period and the average distance from the sun. Now, if we use units of Earth years and the average distance from the Earth to the sun, or the astronomical unit, this works out exactly. If we use different units, seconds and meters or whatever, you need a scaling factor. But if we use these two, it's just the orbital period squared is equal to the average distance cubed. It's pretty nice, right? Makes a nice, easy to follow relationship. But only if you use these two units. For example, what's the Earth's orbital period squared? 1 year times 1 year is 1 year, right? What's the Earth's average distance? 1 AU, right? 1 times 1 times 1 is still 1, so 1 equals 1, it checks out. And it works, believe it or not, for all the other planets. You're welcome to try on your own. But that essentially concludes today's physics lecture. I hope you have enjoyed this lecture as much as I have had giving it. And I'll see you next time. I believe next time we've got a new chapter to start.